Okay, so let us get started. So we have discussed magnetic field distribution for DC machine. First we started with a smooth rotor and saw the effect of only stator winding being excited. So we saw the radial flux lines in the air gap. We also understood the cause behind it. Then we started looking at the radial flux density distribution and tangential flux density distribution along the air gap. So for this case, smooth rotor case, we actually understood. We actually found out the B versus theta distribution to be bell-shaped, which is often or mostly discussed in textbooks. But we also looked at the tangential flux density distribution, and using the Maxwell stress tensor, we understood how to get the radial force density and tangential force density, which told us that if only stator winding is excited, then there are two couples working or acting on the rotor, but they cancel each other, so there is no net torque production. Then we looked at the slotted armature, and that is a practical case because we have to put some winding into the rotor. We stator. So if we look at the zoomed in view, then we understood that flux lines in the from the slot opening region tend to go to the nearby teeth. So that leaves a vacant flux density region at the middle of the slot opening, and on the two sides it gets diverted. So that is what we found, that there are dips in the radial flux density distribution. So these dips correspond to um, the slot openings of the armature. Go on to look at the tangential flux density distribution. It will be, and thereafter get the radial and tangential force density distribution. It will have the same picture, that still there will be no torque production. Then we went on to look at the rotor winding. So uh, due to the action of the commutator and brush, all the conductors which are under one pole, they carry current of one polarity, other conductors carry current of the opposite polarity. So if these are the two poles, so this is the interpolar axis. So any conductor that is above the interpolar axis carries dot current, whether whereas the bottom conductors, they carry cross current. And as the rotor rotates, so the this conductor will, after some, if it is rotating in the anti-clockwise direction, then after some time it may go somewhere here. So when this conductor is here, then it will be conducting cross current, but when the same conductor crosses the interpolar axis and goes upward, or the above the interpolar axis, then it will start carrying dot current. So this is the action of commutator and brush. So first we'll try to understand. We looked at the flux line distribution. This is the magnetic axis in this case, but unlike the previous case, we found that the flux density, the number of flux lines along the magnetic axis, is quite low. And we also understood the reason, because along this axis, the air path is too high. Air path is quite long. So because reluctance, that is 1 by mu naught L by area. So this area, so I'm just concerned about the some reluctance of the air gap portion. So because this length is quite high, so the reluctance is very low. So the high reluctance along that path actually causes the flux density to be quite low. Now at this point of time, let us discuss.
Sir,
Suppose
sorry
we
to
know.
interrupt you. Sir,
Okay.
how A will be considered here? Area?
Yeah, that is what I'm going to discuss right now. Okay, so that is what I'll discuss next. So in these cases where uh, length is quite big, so the air gap, if the air gap length is quite small, then it is quite easy to or assume the flux line um, path, and thereafter we can calculate the area. For an example, if we have small air gap, say if we have a surface, if we have a say a surface a pole like this, which has some surface area. So this is the depth. So this is the axial depth, and this thing, width of the pole that we are able to see. And if we have another, pole uh, directly facing this one, then, and if this gap, whatever is this gap between these two surfaces, if this is quite small, then we can approximate the path to be straight lines between these two surfaces. And we can approximate. Now I will draw a 2D view. So this is one pole, this is another pole. If the gap is quite small, then the lines can be approximated to be lines, may not be exactly lines, exactly straight lines, but they can be reasonably approximated as straight lines gap length, say g. Say if we have this case, then the area is straightforward to calculate. So this is nothing but the surface area that I'm hatching. So this area can be calculated by so this area is whatever this width w, and say the length is l, so the area will be w into l. This is straightforward to calculate. Now uh, for another case, say, do I have some space? Okay, I'll continue here only. So say we are looking at another case. Say we are looking at another case. What is that case? If if the length is quite big, if the length is reasonably bigger compared to the earlier case, then you understand that fringing will be significant. So the flux lines probably at the middle, they will still be crossing like this, but as the lines tend to go on the two sides, then they will tend to bulge out. They will, that is how the actual flux line distribution would be. So they will tend to bulge out. So in this case, it is not straightforward to calculate the area. So in such a case, what is typically done is we assume that the effective area, we still think that the g, the gap, or the length of the flux line, we approximated length, we still can approximate it to be g. And area, we can approximate. There are some like empirical expressions available. Like we will assume if this area is a, say this w into l, then we may approximate it to be some k into a, where k is higher than or greater than 1. So how to calculate this a, k? There are different empirical expressions available. So it is an approximation. You have to understand that. So as the gap increases, it becomes difficult to predict the flux line path of the flux lines. So we it is generally tackled by approximating or assuming some factor which tend to increase the effective area. Or so this is how this type of situations are handled.
Sir, I have a
Now,
doubt.
okay, yes.
Sir, you are saying K is greater than A. then the
K
reluctance
is
will
greater than
reduce,
1.
right?
K is
Ah,
greater than 1.
yes,
Yes.
K is greater than 1 means uh, reluctance will decrease, right?
Yes. So
But
if we do not if you do not consider the side flux paths, and if you only consider that flux lines can only flow in this box, then you are missing out some flux, right? You are missing out the side
yes,
fluxes.
exactly.
So that means you are, if you approximate your flux path to be this hatched blue area or blue box, then or you are underestimating your permeance. So actual permeance is higher, but you are underestimating the permeance. So that means you are overestimating your reluctance. So that means if you actually consider this fringing flux, then your reluctance will actually go down.
Okay. Okay, sir. Okay, thank you.
Yeah, but we are not, you must understand that we are not comparing this case reluctance of
Along the
is quite
magnetic
big.
axis, right?
Along the magnetic axis means, yeah, this
Which we
G
have. No, sir.
gap
Actually,
between the two
what
poles.
I thought is your explanation area will be Ka. I thought you are saying for the along why we have lesser density at at the magnetic axis in the CFD diagram.
Oh, no, 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 I'm not yet there. I'm not yet
Oh,
there.
okay, sir. Okay,
I'm
got
just,
it, got it.
I'm just telling, I'm just discussing. It gets difficult to calculate reluctance directly, or reluctance is an approximation. In the first few lectures probably I have discussed, reluctance is a magnetic circuit concept. So actual magnetic field can be approximated as magnetic circuit for a few cases where most of the flux path is through iron and only a small portion is through gap. Only those cases our magnetic circuit approximation holds good. Like we can quickly come up with flux density, magnetic field intensity, all these things only if our magnetic circuit approximations hold good. What are the magnetic circuit approximation? Magnetic circuit approximations are, if we have some flux path, say if we have a C core like this, only if this, and we have some winding here, only if the flux path mostly flows through iron and only a small portion of the flux length or flux path length is through iron, then only it is possible to represent this magnetic field, or the field for this particular case, as magnetic circuit. Other cases it is not possible. In case the if the gap is quite big, say as big as this, then it is not possible to just calculate the reluctance by assuming some flux path like this and calculate B, then it will be quite erroneous. So our magnetic circuit, it is you have to always keep in mind that our magnetic circuit approximations hold good only in case where there is a very small air gap in the flux path. Other cases it is not valid. We have to do some approximations if we have to, if we want to apply some analytical and come up with some analytical expressions, but straightforward reluctance calculation is not possible quite big, as I have. I'm just, I'm telling that reluctance is quite high. uh, how I am telling and what is the understanding behind that, I am going to discuss right now. So you understand that for cases where uh, the air gap is quite big, then our reluctance expression, or we cannot readily calculate the reluctance, that is not straightforward. So in those cases, what can be done, or I'm just discussing, or I am just telling reluctance along this path to be high in a qualitative sense, not quantitative. So how to if we have to go into quantitative, then how to approach that I'll discuss now. So what is our reluctance? Suppose we have some flux line. Say this is surface 1 and this is surface 2, and we have some flux line between these two surfaces. Say it is like this. Say this is this flux line. So let us assume some flux line with infinitesimal width, say where the width is dx, and say we have some expression for L. L is the length of the line. Say we have, then what will be the reluctance of this infinitesimal flux line, flux path? That will be dr will be equal to 1 by mu naught L divided by, say axial length is still ls, say ls is the axial depth, so the area will be ls into dx, right? This will be the reluctance. This will be the reluctance of this infinitesimal
Sir,
flux.
sorry
Yes.
to interrupt you.
Okay.
Sir, does these flux lines will have some kind of ribbon-like structure or thread-like structure, sir?
I don't understand what do you mean by ribbon or thread.
Ribbon means it will have depth in the page
Yeah,
or
depth is
into the
along the
screen.
page. Depth is into the screen. So
Okay,
I'm considering a 2D case. I'm considering a 2D case where there is no along the axial depth.
okay.
That is the
Really,
that
these
is the case. Hmm.
okay. Really, these will be of we can think of them like ribbon, right?
Yeah, you can think them like ribbon, but whether again, if your axial depth is quite small compared to what is this distance between these two surfaces.
Unable to see that the two surfaces, sir.
So whatever
Okay.
these two surfaces I'm indicating, the two boundaries, say in this case of a machine, so this is the machine, this is the axial depth, right?
Yes.
So our 2D approximation holds good only the cases where the diameter of the cylinder is quite low compared to the axial depth. Axial depth is assumed to be high. In those cases only we can take a cross sectional view and do a 2D analysis on that. Otherwise the 3D effects you have to take into consideration. That will get quite complicated. So as of now, let us assume that all the cases that we are discussing, all the cases they are symmetric along the depth. So if we take a cross sectional view that
Okay.
and assume some flux path that holds along the depth.
Okay. Okay. Got it, sir. Got it.
Okay. So so that means this is the reluctance of this infinitesimal one. Now if there is some MMF, if we know what is the MMF across MMF drop across this between these 2 points, say point A and point B, say MMF is MMF, we know what is the MMF drop across this 2 points. Now what will be the infinitesimal flux flowing through this path? That will be MMF divided by the infinitesimal reluctance, right? Now if I put in the expression MMF divided by 1 by mu naught L by Ls into dx, right? If I put it, then I'll simply uh, this part is separate, So I'll take this dx into ls, that is the infinitesimal area. So if it goes in this side, it will become ls into dx, right? I'll erase this portion. So this portion, so we are left with l here. So this is nothing but the infinitesimal uh, flux divided by infinitesimal area, although it may not be defined in mathematical sense, but if we consider limit, so d phi dx, then this is nothing but d phi dA, that is nothing but an estimate of flux density at this flux density here. So this thing indicates what is the flux density here. So I'm following a very this is not uh, uh, very much true mathematically, but because two infinitesimal quantities, you cannot divide it like that. That is the thing. But if we do this, or this is a measure of flux density, that is what I am trying to say. This is a measure of flux density. So if we have the mmf information along uh, for between 2 points, and if we have some approximate length of flux line between the two, then we can get an expression for, we can calculate the b by simply divide or using this expression. So if we divide the mmf by L and multiply it with mu naught, then we have an expression for B. This is not mathematically um, or exhaustive, because we are dividing two infinitesimal quantities. This I followed just to tell you that this is coming from, or the reluctance is somewhat related to this. The more mathematical way or approach to reach this will be applying Ampere's law. So assume that this is a contour, part of the contour. So H dot dl equal to uh, the mmf. So if you assume the total flux path, then, and if you know that uh, what part of mmf actually gets dropped between these 2 points, so that tells you that H into L, that is nothing but the mmf. So H equal to mmf by L, and if you want to get the B, then you have to multiply by mu naught. So mu naught into mmf by L. More correct way to get to this expression. So what have we achieved by this discussion? That at any point, if we know between two surfaces, if we know what is the mmf drop between the two surfaces, and if we have an approximate expression for L, the length of flux line between the two surfaces, then it is then it is possible for us to calculate B. So for this, what do we need, we need to have MMF distribution along the air gap. That is what we derived uh, 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 in some way in the last class, and we are going to discuss it again. So now I discussed why MMF distribution is important and how we can get B distribution from MMF distribution if we have the expression of L. So yeah, that is going to be an approximation. So this is a zoomed in view of the flux line distribution for a case where only armature winding is excited. Now let us try to take different contours and try to get the mmf distribution, and from there we will be able to appreciate why the B distribution was like that. whatever we saw earlier. So in this case, if we consider this to be 0 degree and this to be 180 degree, then how many tooth, what is the tooth pitch here? So 1 2 3 4 5 6 7 8 9. So total we have 9 things. So if this is 0 degree, it will be 20, 40, 60, 80, 100, 120, 140, 160, 180. These are the angles uh, at these different points, right? At these different points. Now, this 0 and 180 degree, that is along the axis of the magnetic field. So if we move 90 degree, that will be the point where no flux line will be along this, or the direction of the flux line will not be along this line. So this is the interpolar axis. Now if we take any flux line, say this one, we have, then one side you say, so first thing that we already have discussed, that if each slot is carrying some current, say I, and say for this, for simplicity, all the slots are having only one conductor, then what is the MMF enclosed by this, or the current enclosed by this flux line? That is I. Now if this is MMF I, then half the MMF gets dropped on one side and another half gets dropped and on the other side. Now if you consider it to be dot, then the flux line direction will be anti-clockwise direction. So on the right side it will be going up and the left side it is going down. Now if we construct a magnetic circuit corresponding to this, it will be, this portion indicates the reluctance of the iron, which is very low. So I am indicating, I am assuming it to be short. Then we have some reluctance corresponding to this small air gap, and again some reluctance corresponding to small air gap. And this is of course, again this is closed to the iron, which is again short, and the flux is driven here. So I have to indicate a plus minus like this, so that the flux direction is indicated by this. So if total MMF here is I, then MMF drop here on this side will be I by 2 in this polarity, and on the other side the MMF drop will be again I by 2 in the opposite polarity, right? Now MMF by length, that is a measure of H. MMF by length of the air gap, or the flux line through air, whatever is the length, that is, if that is L, then H can be expressed by MMF by L, because H is a vector and it is same as, the direction of H is same as the flux line's direction. So let us take the same approximate or assumption, or the same reference direction for um the sign of H, or the direction of H. So we have been assuming that if flux lines are radially outward, then we'll consider the B or H to be positive, and if it is radially inward, then we will assume the B or H that we have been taking. So following this assumption, for the right hand side, that is around this 80 degree, we will have plus I, because flux lines are actually radially going out, and around this 100 degree we will have minus I by 2, because there the flux lines is coming radially inward. So if I try to plot, So this is the horizontal axis, this is theta, and this is the vertical axis. This is the vertical axis. It can be MMF or it can be H also. So for now let us plot MMF. So now you understand what do I mean by signs or positive and negative MMF when I mention plus I by 2 or minus I by 2. That is related to the detection of the flux line and our convention taken. So say this is 0 degree, this is 0 degree, and we have up to 180 degree. This is
Sir, in the
90
last
degree.
class we have discussed the same, right?
Yes, correct.
Is there any
But there,
difference?
I don't think it was. And I felt there may be some doubts because of that. That is why I am discussing it again.
Okay, sir. Okay, thank you.
Yeah. Last day, yeah, there was not enough space to discuss it. So this is 20, 40, 60, 80, 100, 120, 140, 160, 180. Now our magnetic neutral or magnetic this uh, interpolar axis is at 90 degree. That is the interpolar axis. I am indicating with dotted line. Now if we take a flux line like this, whatever I have indicated, one side I have to indicate the MMF drop is plus I by 2, and other side we have minus I by 2. So let me indicate some vertical lines also. Say I by 2, minus I by 2, I, it will be say 2I, 3I, like that. So this will be minus I, this will be minus 2I, this will be minus 3I in this manner. If we take any flux line that is at 80 degree and 100 degree, then you can understand that at 80 degree we'll have plus I by 2, and at 100 degree we'll have minus I by 2. So let me plot it at 80 degree plus I by 2 and 100 degree minus I by 2. Now even if I take a flux line which is like this, you can understand that it is enclosing the same current, so it will still be same, it will same be the same. So if I go on the two sides of 80 degree and 100 degree, then it will be constant at I by 2 only. Now if I go next, now quickly I can complete it. If I go next 60 degree and 180 degree, what is the current enclosed is 3I. So on one side we'll have 1.5 I, another side we'll have minus 1.5 I. So 60 degree, this is 60 degree, this is 1.5 I. So we have it here, and 1.5 I, 120 degree, we have it here. So this is the MMF distribution. MMF distribution, and there is some discontinuity at the slot opening. So only if you spare the slot opening regions, it will be stepped waveform, a stepped distribution like this. If I go again to the third case, it will be 1 2 3 4 5. So 2.5 here at 40 degree, and again 2.5 at 240 degree. Again if I go next, here is the main thing, or here may be the confusion. So I have to take a flux line like this, whose length through air gap I may not know. That may be, if I go back here, That may be some line like this, whose length is difficult to calculate. I think you understand that it is quite difficult and there is no expression for that, but still, whatever the line length be, the MMF drop across that line will be the same. That is, here it will be um, 3.5 into I, and finally where all 9 slots are there, it will be minus plus 4.5 into I and minus 4.5 into I. So that is the distribution. And in the slot opening region there will be a dip, so this dip can be joined by a line with certain slope. So this is the MMF distribution that you will have, and the same distribution, the same thing will repeat. So it is symmetric. So if I complete it, then it will be like this. It will be uh, whatever I'm trying to indicate. It the MMF distribution is like this. Now this is about the MMF distribution. What about length? Because we just saw that if we have some expression of L at different angles, then if we simply divide the MMF by that L, we'll have the B distribution if we multiply it by mu naught. So what is the G? What is the G when there is overlap, or what is the G where the stator pole and armature, they are facing each other? It is only a very small air gap, that is G. I'm neglecting the slot opening region. So actually, if you look at the air gap as a function of theta, or air gap length as a function of theta, then say here all these places under where the stator pole is facing one rotor tooth, there it is G, it is always constant. Now at the slot opening region it will be something higher than G. You understand that it is not G, it is not very high also, but it is some value significantly higher than G. That is what I think you can understand. It will be something like this, some bigger length. Again, when you go to the next teeth, again it is a very small air gap G. So if I plot the variation of G, some length, so Lg along theta, then wherever there is overlap, there it will be very small thing, say like G, and wherever I have the slot openings, then there will be some increase. How to express that increase? That is difficult, but you can have a feeling that there will be an increase, effective increase of the length of flux line through air gap. So that
Sir,
is
I
what.
have a doubt. Hello.
Yes, go on.
Sir, at teeth means we can say that it is the path through which the flux line is going, right? In the air
Correct.
gap.
In the air gap, yes.
But at the slot opening,
Yes,
as per the diagram, there is no flux line flowing.
correct.
Then how we can take the length of the air gap there?
See, any flux line distribution that you are having, you in the software you are supposed to put that how you want how many flux lines. So it is always the number of flux lines is always relative. I can increase the lines that I want to plot. So as per the density, it will get distributed. It is always relative. I hope you understand. So if I now I have plotted for certain number of lines, if I increase that, then you will start seeing some lines like this that may go like that may uh, that may flow to the slot and go into the slot walls. You may start seeing some lines like that.
Okay, sir, got it. Thank you.
Yeah, so that is what I mean by the length of flux line in that part. But those are higher, you can have that sense, right? The length of
Yes, sir.
flux
Yes,
lines
yes.
through slot
It's
opening,
clear.
that is higher. That is higher.
Clear, clear, clear.
Yeah. And when you actually go in these regions where flux lines are actually flowing from the rotor teeth to the stator yoke, then the length is quite high, quite big, and the length, we do not have any expression for that because it's difficult to have, but the length will be quite high. Length can be quite high like this. So it can be approximated as the radial distance between the yoke and the stator, or the rotor's outer diameter and the stator yoke. That can be one approximation. So the length can be approximated by that line, right? So this is the LG. Now you have one you have some idea of how LG varies with theta, and if you divide this MMF by that LG distribution, whatever I indicated, you will see that you will get this distribution. So let us try to make sense out of it now. So this is 180 degree and this is 0 degree. This is the portion that I have for which now here. So from this point, that is the stator pole, wherever our stator pole is, from this point onwards, this angle to this angle, whatever these angles are, in between that is in between these two angles, the gap is very small, say G, and slight increase in the slot opening region. So that is why in this region, say from here to here, whatever this region is, whatever the angle, what is the angle here, this is 40 degree. So say 30 degree to 150 degree, 30 degree to 150 degree, maybe from here to here. In this region, whatever is the shape of the MMF distribution, the same shape is retained. So 30 degree somewhere here to 150 degree somewhere here. You can see that the same stepped kind of a distribution in B radial, because anyway the flux lines are radial only when there is a small air gap. That same pattern is visible. You can see the pattern. The same stepped kind of pattern, whatever we derived for MMF, that same is visible here. But in this region, where the length of flux line increases rapidly, right, like it's very high, very big, it's approximately the whatever is this length of the or this height of the stator pole, it goes to as high as that. So for some sample values, the height can be say a few millimeters to tens of millimeters, say 20 mm, maybe one dimension. But the G, where they were facing each other, that may be only 0.5 mm. So it is the length is higher by 40 times. So if B was something, it will be 140. So 140 times compared to the B what was there in the case for where G was only 0.5 mm. This is a rough approximation, rough estimation. So that is why you can see that although the MMF at 0 degree or closer to 0 degree or 180 degree or closer to 180 degree is very high, or actually at its peak, but or the flux density is quite low in these regions, and the pattern does not hold because whatever is the MMF, that is divided by at least a very big number, say 20 mm, whereas it was divided by only a small number, say 0.5 mm earlier. Now it is divided by, it's getting divided by some big number, so 20 mm. That is why I think you now you have some sense of this distribution, why the B distribution is the way it is. We discussed it directly last day, but now I think it gives better clarity. So do you have any question regarding this? So it is general rule to, or general procedure to find out B distribution. So for an example, if I try to now do it for the field, if I try to do it for the field, so this is the axis, right? So we have to, if we take any flux line like this, then we understand that MMF distribution, or MMF drop, half is here, half is here, and total, say this is IF and this is also IF, so 2IF, that is the total current enclosed. So IF gets dropped here and IF gets dropped here. So if even if we take some other flux lines like this, all throughout like this, any flux line in the upper 180 degree to this lower 180 degree, any flux line if we take, all the flux lines will have MMF equal to so MMF distribution will be basically IF will get will be, and minus IF will be there continuously on the lower thing, plus and minus depending on the direction obviously. If it is dot and if it is cross, flux lines will be upward, so it will be plus on the upward side and minus on the downward side. Now what about length of flux lines? Length of flux lines is quite low. It is only G under 1. It's quite big. It is quite big. That is why, although the MMF distribution, if it is plotted, it will be something, a perfect square wave. It will be plus some value from 0 to 180 degree and minus some value from 180 degree to 360 degree, because the length, effective length in this region, interpolar region, that is quite big. That is why there will be a sharp decline in B distribution in these regions, whereas the B will be quite high under the pole. And again, at the slot opening, because there is some effective increase in the L length, so there are some dips in the slot opening regions. So the same principle can be applied anywhere to get the B distribution. So the steps are, first you have to get the MMF distribution, MMF versus theta. Then you have to get uh, some sense of Lg versus theta, length of flux line through air gap versus theta, some sense of this, high low, where low, in that way. It may not be quantitative. And then if you simply divide, so at a given theta, if you know what is the MMF, if you divide it by Lg and multiply by mu naught, then you will get the B at that theta. That is how to get it. Okay. So if I indicated last day that if we actually look at the tangential component, then there will be many sharp edges at all the slot openings, and wherever there is some corner in the magnetic of the magnetic steel. So this is a corner. There we expect some edge. All the slot openings are having some edge. So so we expect the B tangential that it is full of some edges in all the slot openings. Next, if we actually apply the um, this uh, Maxwell's stress tensor to get the radial force density and tangential force density, we'll be able to see that we get wherever we have higher flux density, there we have higher radial force also, and radial force is always positive because radial force, the direction indicates the force acting on the rotor. So because it's north and south, the rotor will always experience force in the outward direction because it will get attracted by the south pole nearby it, as indicated here. The stator has south pole, the rotor has north pole. So the rotor north pole will get attracted by the stator south pole here. Uh, so this is how the radial force density will vary, and tangential force density, if you simply multiply point by point, then you will get this tangential force density. And in this case also you can see that there are multiple couples acting on the rotor, but there is no net torque production because whatever this edge, that same edge is nullified by this whatever is this couple, so 180-degree couple, so that is nullified by another couple in the opposite direction. You can actually go point by point and actually see that tangential force does not have any DC positive net DC component in this case. So if you have only armature excited, then also you will have no net torque production if only armature is excited. Now, so probably I will just introduce this. So if both the stator and rotor are excited, then what happens is what we are going to discuss. So this will be
Sorry to disturb you,
okay.
sir.
Okay.
That radial flux density is clearly established with MMF, but for tangential flux density, whether we can define with respect to MMF, sir?
No, no, no. We cannot define with respect to MMF. It is not possible. Tangential force density is quite low, and no, it is not. Analytically, it's very difficult to get the tangential flux density.
Okay, sir.
It can only be done like this, that if you will draw some circle along the air gap and get the B vectors, get the components of that, that is the only way. Analytically, that is not possible.
So tangential H also will be there, sir.
Tangential H also, because B is there, tangential H is also will also be there. Yes, that very difficult to get.
Okay, sir.
So this scenario will other machines also, like for all machines like synchronous machine or induction machine, we have discussed the stator magnetic field and rotor magnetic field separately. That is what we have done till now. That stator magnetic field, we have understood that it is along this axis, vertical axis, and the rotor magnetic field, we have seen that it is along the horizontal axis. So there also induction machine or synchronous machine, we had two fields. We looked at the two fields separately. Now for the first time we are going to see what is the uh, what happens if there are two fields simultaneously exist, and how they interact, and how that translates to force production. So that the same thing, if that is done for the other machines also, similar uh, results or similar things we will get, that if only one field is excited, then there are some radial forces, there are some tangential forces, but they will cancel each other so that there is no torque. But if the two fields they exist simultaneously, then they will interact with each other and they will lead to some tangential force production, which are not and there will be some net torque. So we will try to look at that. So I think I'll stop here only. We will look at that afresh on the next day. Okay. Any question from whatever I discussed? So most portion was recapitulation of yesterday's or the last day's portion, but I think we discussed it with clarity, discussing all the steps, MMF distribution, gap, length of the gap or air gap flux path. Then how do we get B? Yes. Any question?
Sir, just out of curiosity, I'm asking, sir, how many classes it may take to enter the topic dynamic modeling?
I hope that the DC machine, whatever I am discussing, that will get finished by the next class, because after that there is nothing else. Then we will discuss whatever field solution we have discussed, and from there we'll get into the circuits, like the electrical circuits. We'll have a sense of inductance. We'll have a sense of inductance. So that is the next step. After we understand the field and torque production from field, then we will get onto that.
Okay, sir. Thank you
Now,
so much.
now I think you already can tell. You have armature winding and field winding. Which winding do you think that will have higher inductance? Can you answer that?
Which winding? Rotor winding?
Which one will have higher inductance? So inductance is nothing but number of turns squared divided by reluctance. Some simplified reluctance. So which winding do you think sees higher reluctance, and which one sees lower reluctance? You can simply think as per along the axis.
Okay. Along the axis means the reluctance of rotor is high.
The rotor winding, the armature winding sees higher reluctance along this
Yes.
axis. So the RA is very high compared to RF, because RF, this is the axis of the field, so you have a very small air gap only. So one thing we understand that RA is very high compared to RF. So if both are having the same number of turns, then LA will be very low compared to LF. But actually, do they have very different or what is the relation about number of turns? All those things will come step by step, and from there we'll go to the electrical equivalent circuit.
You are saying it may take two more classes, right?
I'm telling that in after one class, probably next week, we will be starting to realize the equivalent dynamic equivalent circuit of a DC machine.
Okay. Okay, sir. Actually, your classes are so interesting. Uh, we are really curious to enter that concept as they are not available anywhere else in,
Yeah, yeah, that
in
is
such
true.
a detailed manner, sir. So we are expecting soon them.
Okay.
Sir,
Yeah,
one more
there is no
doubt.
deadline. Yeah.
Sir, regarding that MMF part which you have plotted,
Mhm.
uh,
Yes,
here in that we are taking the ampere's law, right, sir?
we are taking the ampere's
Ampere's
influence.
law. So with respect to each slot, we are taking the current, right?
Correct. We are assuming that I current flows through all the slots, and there is only one turn, only one conductor. That is the assumption here.
Okay, sir. So I current will be always positive in means positive in that sense, sir.
Yes, because we are only looking at the upper 180 degree, so all the currents are dot. If we look at the currents or the slots in the bottom 180-degree portion, it will be cross, that is negative. So here I have only plotted for one one half. So if you do the same thing on the bottom side, there you will have the current polarities to be negative, and there you will have um, its effect, whatever it may be.
Actually, sir, if we consider the upper half alone,
Hmm.
then in the last one that is around 0 degree, the
Yes,
whole thing will come up. Like
correct.
if we are considering the whole 9 thing, it will be 9, right, sir?
Yes. So that is why 9i, and half
Ah,
of that gets dropped in one side, half of the gets dropped on the other side. So that is why plus 4.5 and minus 4.5.
okay, okay, sir.
And if
Fine.
you even consider 9 cross, so say 3, 4, 5, 6, 7, 8, 9. So say these are the 9 cross conductors. If you have to again go like this, so you have to first take this, then this is cross. So because of cross, it will be clockwise direction. So this side will have, this right hand side will have positive, and left hand side will have negative, because it is radially, this is the surface, it is radially going outward, it is going radially inward. So similarly, again you have to take this, again it will be outward, it will be inward. Here we will
Oh,
find out that it is the same direction. Here also it is going outward, here also it is going outward. That is why you will have the same thing. 0 degree, you have the positive. 0 degree or 360 degree, both are the same thing. So you have the positive maximum here and negative maximum at 180 degree. That is why it is sufficient to draw for only one half,
okay, sir.
because it's symmetrical. Okay, let us close now then. Thank you for attending.
Thank you, sir.